In this video, we're gonna cover the second half of the 1-2 punch of Griddler 2.5, which is simulating the solar cell that you've created using the design interface. So we're just gonna fly through straight from the beginning here. Let's make a solar cell out of a square wafer, like a multicrystalline cell. 3 bus bars is good. It's gonna make minimal changes to the pattern. Okay, so that brings us to this screen here that gets us ready to parse the pattern into a format that can be simulated in the finite element code. So you'll notice here that the workflow is just very straightforward. You press the buttons that's available. So the first thing that happens is analyze front. So what happens is Griddler will run over all the shapes and merge them together into one giant contour. Next, we hit mesh. That's gonna define the nodes, and as well as split up the entire plane into many triangles, as you can see here in the zoom in view, where the length of the finger is divided up into many segments, and in between the fingers the emitter has been divided up as well. So the vertices of the triangles, the nodes, is like a current source and a diode combination, and the sides of the triangles connecting the nodes together are like resistors. So that forms the network model of the solar cell, which is then iteratively solved for each voltage. Now you can decide to play around with the mesh detail, both in the directions tangent to the metal as well as perpendicular to the metal. So here we just have the default settings, which is medium, and that suffices for our work, for the number of fingers that we have. So we click OK, and that gets us to the rear side. Same thing, we analyze the rear, meshes it. The rear requires less points because most of the area is metal. Metal is very conductive, and it's not expected that the voltage variation will be very much over the rear side, and so we don't need as many nodes. So we hit OK. Most of this stuff is automatic, and that brings us to the simulation screen already. So much like the design H pattern screen, the simulation screen has this space here where you define all the solar cell device parameters. So remember, the design screen is where we define much of the geometry. Here's where we define the underlying physical parameters to the solar cell. The parameters are divided into two halves. On the left, we have mostly everything due to the front side or the front plane. For a lot of solar cells, that is the emitter plane. On the right of it is a column where we define mostly things that are related to the rear side of the cell. Well, what kind of properties do solar cells have? Up the top here we have metallization parameters. So these are things like finger sheet resistance. Some people would define it by the bulk resistance of the material while specifying the height of this layer. Alternatively, we can define something called the sheet resistance. So for example, for silver fingers on the front side, the metal sheet resistance is typically about 3 milliohms per square. On the rear side, it depends. If it is here in this case an full area metal, the metal being aluminum, then typically we have something like 10 milliohms per square. Busbar sheet resistance applies in the case when the busbar layer is printed separately from the finger layer, such that they are not the same material. For example, on the rear side, the busbar layer is printed in silver. It might have a lower metal sheet resistance. Let's say here we put 3 milliohms per square. And then next we have something called a finger contact resistance. This parameter summarizes the resistance existing at the contact of the metal semiconductor interface. For the front silver print, this number is often sitting around 1 to 3 milliohms centimeters square. So we're just gonna put 2. For the rear aluminum contact, it matters not as much because the rear side has much larger contact area, so that even a poor contact will not affect the flow of current as much. We're just gonna leave it at 0. Next, we have something called the layer sheet resistance. So for the front side here in this example, it could be the emitter sheet resistance. This may be a p-type multicrystalline solar cell, so we're talking about the emitter being a phosphorus dope layer. This layer typically nowadays has a sheet resistance from 80 to 90 ohms per square, so we're just gonna leave it at 80. Rear layer sheet resistance in this case may refer to the P layer, which is the wafer itself. So it may take on a value of something like the sheet resistance of the wafer itself. Next, we encounter something that is internal to the wafer, and these are called wafer internal series resistance and shunt conductance. Series resistance of the wafer may refer to the fact that the wafer has a finite thickness, maybe 180 microns, and it has a certain bulk resistance, and so current flowing through the wafer will encounter a certain series resistance. But its effect is usually small, so we're gonna just leave it at 0. Shunt conductance may occur, let's say when there's a processing problem. Let's say the front metal print has silver spiking through the PN junction, causing a short-circuiting pathway, in which case the shunt conductance would be greater than 0. But in this case, let's say the processing is ideal, and so we don't have any shunt conductance, so we turn it also off to 0 as it is by default. Next, we encounter something called metal optical transparency. Now, metal layers are typically not transparent in the sense that light can pass through them, but they may be a little bit to the extent that they can reflect light and scatter them into the cell. If we set the value to 0 as we do now, for example, for front metallization fingers, we have set the value to 0. We imply that the physical area of the front grid equals the area in which the cell is shaded from illumination. So we can see here for this particular grid we've designed, the wafer area in total is 243.36 centimeters square, and with that the optical shading, which is this physical area of the front grid, makes up 6.24%. If alternatively we turn up the transparency, implying that a certain amount of light, in this case 10% of light, which reflects off the front grid, can actually be scattered into the cell and be collected as light, then the optical shading drops to 5.62%. If the cell were encapsulated in a module, this metal optical transparency may be even greater, because light which is reflected off the front grid has the ability to scatter multiple times in the space between the cell, the encapsulant, and the glass inside the module, giving it much greater chance to reflect into the cell. So for module, this number can be as high as 0.5, but for this example here, we'll just leave it at the default, which is 0. Next, we encounter the front current extraction and rear current extraction. So by default here, we have something called extract current at each probe point. And what that really means is each of these blue X's along the bus bars on the front side is set to the terminal voltage, and current is being extracted at these points. So this is very similar to the situation you would encounter when the cell is under an IV testing stage, where probe pins are aligned to the bus bars at these points. Alternatively, we can choose solder ribbon at probe points, extract current at ribbon ends. If we choose that, we get something like this, with the yellow rectangle being the ribbon connecting from one cell to another as you would typically have it in a module connection. So in this case here, what happens is current still flows out of these blue X's, but after that the current has to continue its journey down the ribbon all the way to the end of the wafer. And the terminal voltage is set at the end of the wafer. So that would be the typical connection you get in a module. So here, for the time being, we set it to the default to simulate the cell under IV testing conditions. Contact points resistance means the contact resistance of the probe pins that are pushing against the bus bars at these probe points. This is more of a very detailed definition, so for the time being, we just set it to its default value. Next, we get to very important parameters. They are called the diode parameters. So remember that a solar cell can be described by an equivalent circuit model consisting of a light-induced current source and diodes. And one way to do that is what's called a two-diode model, where the diode characteristics is described as being the sum of an n equals 1 diode and an n equals 2 diode. So Griddler also uses this equivalent circuit model, except that instead of the entire circuit consisting of only one set of light-induced current source, diodes, and resistors, it's actually representing the entire solar cell by a vast network of interconnected current sources and diodes interconnected together by resistors. So under this scheme, if we were to suppose that all the light-induced current sources and diodes are taking on the same values per unit area throughout the entire cell, then these parameters will be defined in this area here. The light-induced current source on the front side is described by the 1 sun light-induced current density in the non-shaded area. So that's referring to the space in between the fingers in this case, the active area, when illuminated with 1 sun of intensity, how much light-induced current density that it generates. So here we're just gonna leave it at the default value of 39.6 milliamps per centimeter square. The value for the rear side just means if there is illumination from the rear side onto the non-metal regions, what would be the light-induced current density? But here is less relevant because most of the entire rear side is metallized in fact, so the metal is blocking out most of the rear side from illumination anyway. And we might decide not to have a simulation of the cell with any rear side illumination, and so this value is irrelevant at the moment. Next, we come to the n equals 1 and n equals 2 diodes. So they are called J01 and J02. And it is useful to split them up so that they take on two different values depending on whether you're talking about the space between the metal under the passivated region or under the metal contact, which often takes on a different value. So at least it is very useful to split up these J01 and J02 numbers according to the region, whether it's a non-metallized region or metallized region. The rear plane of the cell has its own set of numbers, so that you may think of the J01 and J02 having contributions from both the front plane and the rear plane. What that means is, suppose I'm at a location that is between the front fingers and I look at the diode there, the J01 will be equal to 200 femtoamps per centimeter square, which is its value that it takes at the passivated area, plus 0, which is the value contributed by the rear plane over the metal contact, which is at that location over the aluminum rear plane. So one must think of the J01 and J02 of the diodes as being the sum of the contributors from the front plane and the rear plane. So the physical meaning may be the contribution from the front plane is the emitter J0, meaning the emitter recombination current, plus the base recombination current density, which can then be attributed to the rear plane. So in this case, we might decide to have separate numbers for the front and the rear, let's say making up numbers like 80 and 120, and that would have the same effect as 200 and 0, because in either case the sum of these two numbers are the same. So in Griddler, we kind of loosely attribute these J0 numbers either to the front plane or the rear plane. So it's fine to lump the entire J0 onto one side, although some might prefer to actually make a more kind of physical separation where the front J01 refers to specifically the emitter contribution and the rear plane J01 specifically refers to the base combination current, for example. But I leave that choice to you, and a lot of times when you, for example, open the example file of Griddler, or you look at the default settings, oftentimes all the numbers are lumped to the front plane, as you see right now. Next, we got something called edge recombination, J01, J02. So again, these are the two diodes that describes the node, except these are the specific nodes that are located right at the edge of the solar cell, meaning the wafer edge. And you'll notice that the units is defined in femtoamps per centimeter and nanoamps per centimeter. So they're defined per unit length of the edge. This is due to the fact that oftentimes it's observed that the edges of the wafer take on a higher recombination current density. So if you would like to take that into account, you would enter a value which you know into this box. So altogether, these 10 boxes related to J01 and J02 completely describes the recombination characteristics of the device. So we're just gonna leave them right now to the default values. Finally, at the bottom here, we have the front and rear illumination intensity as measured in suns. So we're just gonna leave it at the default so that from the front side we have 1 sun of intensity incident on the cell. From the rear side we have 0. Maybe the rear side of the cell is facing chuck and therefore not receiving any light. So we took an awfully long time to explain these parameters. I bet you would like to see some action. So let's run the IV curve by finding JSC, VOC, MPP. So Griddler will first run a simulation of the current flow pattern under the metal contact to simulate the effect of the contact resistance, after which then it will run the IV curve looking for first the open circuit voltage and then the short circuit current, and finally iteratively looking for the maximum power point. And after which it displays the main IV parameters. You can see that the parameters are based on the inputs that we gave in terms of the metallization related resistances, current extraction method, diode properties, and so on. The VOC is 658 millivolts, maybe too high for a multicrystalline cell, but that just has to do with the particular values of J01s and J02s that we have chosen. They're a little bit too low for a multicrystalline cell. JSC is about 37.13%, so that's pretty much the 39.6 milliamps per centimeter square that we've chosen to be the 1 sun JL in the non-shaded area after we have discounted the optical shading. The fill factor is 80.07%, which is pretty good. And the efficiency is 19.57%, which is awfully good for a multicrystalline cell. So I will be really happy if that were a multicrystalline cell. But anyway, this is the example here. After this, we can have a quick look at the power at maximum power point, as well as the different power losses, dissipations. So here on the left hand side we have output, with the power output here, which is the 19.57 milliwatts per centimeter square in yellow. And then the rest are power losses. So we have the blue, which is the front shading, and then we have the front resistive loss, and then we have rear resistive loss, which is too small to be seen here. And then finally we have all the recombination loss, which we've attributed to the front side. We can also split up the slice. So this green slice, which is front resistive loss, can be further broken down into 3. They are the semiconductor resistance, so that means the emitter sheet resistance loss. Then we have the finger resistance loss, and finally the contact resistance loss. We also have a very small loss on the rear. It's not very much. In the rear aluminum layer, current having to flow along it to the solder pads. And then finally, if we have a look at the front recombination losses, which is all the recombination losses in this case, then they're split up according to the n equals 1 and n equals 2 diode currents happening under the passivated regions and happening under the metal regions. So that's at a glance the various power outputs and losses. We may also save the results, so that's by clicking report. So we can overwrite this demo cell IV and have a look at it. So the report summarizes what we have seen. It has the cell parameters. Here is the wafer area, front metal contact area as in centimeters square, as well as in percentage, as we have seen. Same thing for the rear metal contact, which is pretty much the entire rear. The front and rear optically inactive area, that means the shading area, is pretty much the same as the front metal contact area because we have set the metal transparency to 0. Next we have the IV parameters. So we're first given the light induced current density in the non-shaded regions, which was our input. After the shading, then we result in the front light induced current density overall, which is 37.13 milliamps per centimeter square. That is pretty much the same as the JSC of the IV curve. We also have the VOC, fill factor, efficiency, VMP, IMP, JMP, which are the voltage and currents at maximum power point. And then we have the power analysis at the terminal voltage corresponding to maximum power point, which corresponds to the bar charts that we saw. And finally at the bottom here we have the JV curve consists of the points that were traced. So if we hit find JSC, VOC, MPP, Griddler will just find these 3 points along the IV curve and stop there. If we want a more detailed IV curve, what we do is we can do a JV sweep, and that will enable us to fill in the points in between. So for example, from 0 to 500 millivolts by steps of 50 millivolts. If we do that, then Griddler will just find additional points on the IV curve on top of the points that it has found. And then we may decide to fill in the points near VOC. So now that looks a bit nicer, and if we now save as report, it will save the IV curve with however many points that it has. We may also decide to visualize the voltage distribution, for example, at any arbitrary voltage, for example at MPP. So at MPP we have 559 millivolts, so we can enter that. And in this case then Griddler just solves 1 point and then displays the detailed results in the form of a voltage map, as you can see here. We can also look at in terms of the rear voltage distribution here and the front voltage distribution separately. We can also look at what happens at open circuit. All we need to do is, instead of a number, we enter OC in capital letters in this box and we run, and it will calculate at open circuit what happens. What happens is a much flatter voltage distribution, of course. So now, last but not least, don't forget to save your work. So let's call it a demo cell. And that will save all the results, as well as the cell parameters that you see in the screen, as well as the geometry of the cell that you have designed, so that next time we just need to load session, look for the demo cell that we created, and we're in business.